talk about quick derivatives. Now, I have made a video about long derivatives in the past, which you may want to watch, and I've also made videos about the 6 trigonometric functions and logarithms, which could also be useful. Now, quick derivatives are not only faster, as the name would suggest, but they're also much easier. Alright, now I'm going to start with short derivatives. And to explain these, I'm going to need a general function. And for this, I will use x to the nth, where n is an exponent. Now, we want to find the derivative of this, and we indicate that by writing d over dx in front of it. Now, this means we're taking the derivative of some function, in our case x to the nth, with respect to some variable, in our case x. Now, this bottom part indicates what variable we're taking the derivative of. And it only really becomes important when we start working with functions that have multiple variables in them. However, since all of my functions will have a single variable in them, we don't really need to worry about that. But as for the derivative itself, what we do is we take our function and we subtract 1 from the exponent, and we then multiply that function by the exponent we had previously. So, for example, we'll have x, and then to the n minus 1, because we subtracted 1 from the exponent, and then that will all be times n, because we multiply it by the exponent from up here. So, the derivative of x to the n is n times x to the n minus 1. So, for an example of that, let's use x squared. Now, we're going to find the derivative of this. So what we do is we have x, and then 2 minus 1 is 1. And it gives us x to the first, which is just x. And we then multiply x by that exponent, so the derivative of x squared is 2x. And if you remember my video on long derivatives, you might know that the example I used was x squared. And when plugging it into the long derivative formula, we got 2x. So this process does in fact work. Now, there's another thing I want to mention, and that's if we have a coefficient in front of there. So let's say we have the coefficient a times x to the n. What we do for this is we take the coefficient out, then we take the derivative as normal, and then we multiply the coefficient back in. So, for example, let's say we've got 3x to the 4th. What we do is we'll take the coefficient out, and we'll take the derivative then of just x to the 4th. So, we'll subtract 1 from the power, giving us x cubed, and multiply it by this exponent, so that gives us 4 times x to the 3rd. And then we'll multiply it back by the coefficient. As such, the derivative of 3x to the 4th is 12x cubed. And this is the basic way on how to do short derivatives. Now, I do want to mention that if you have a constant and you take the derivative of it, by the way, I do want to mention that due to the general amount of time it will take to write out the derivative symbol for each of my functions, I will not write out the derivative symbol for each of my functions. But keep in mind that when I have a function and I'm saying I'm going to take a derivative of it, there should be this in front of it. Just to save time, I'm not going to include it. But nonetheless, if you take the derivative of a constant, you will always get 0. This is because a derivative is slope. That is what a derivative is ultimately finding. So, when you take the derivative of a function, you have a function that will determine the slope of your original function at any specific point. Watch my original video on long derivatives for a better explanation on this. Now, the reason a constant has a derivative of 0 is because if you graph a constant, it is just a straight, flat line. It has no slope. As such, its derivative is 0. Now, there are some functions that you cannot find a derivative of using the basic method of quick derivatives. The most notable of these are the trigonometric functions. These do, however, have quick derivatives of their own. And to go through these, I'm going to start with what I would consider the most basic trigonometric function, sine of x. Now, the derivative of sine of x is cosine of x, which is a perfect transition into the derivative of cosine of x, which is negative sine of x. Now, you may be able to figure out, using the coefficient method I highlighted in the previous clip, that the derivative of negative sine of x is negative cosine of x. And the derivative of negative cosine of x is sine of x. So, as you can no doubt see, the derivatives of sine of x and cosine of x go in a bit of a circle. As for the other four trigonometric functions, they don't have that same cool pattern to them. You pretty much take the derivative of them, and then it just stops there. For example, the derivative of tangent of x is just secant squared of x. And the derivative of cotangent of x is negative cosecant squared of x. Now, I mentioned secant and cosecant, so of course we're going to look into those derivatives. And the derivative of secant of x is secant of x times tangent of x. And the derivative of cosecant of x is negative cosecant of x times cotangent of x. So these are the quick derivatives for the 6 trigonometric functions. Now, there are other functions that have their own special quick derivatives. One of those is logarithms and its associated functions. To explain these, I'm going to use the generic function b to the x. Now, notice the distinction between b to the x and x to the n. In x to the nth, x, the base number, is variable, while the exponent is constant. However, in b to the x, the base number is constant, while the exponent is variable. So, if we're going to take the derivative of a function with a variable exponent, what we do is we take the natural log, as denoted by ln, of the base number times the function. So, the derivative of b to the x is the natural log of b times b to the x. Now, as for logarithms, let's say we have logarithm base b of x. Now, for the derivative of this, we take 1 over the natural log of b times x. So the derivative of log base b of x is 1 over natural log of b times x. Now, say for example, we plug in e for b. This is a special case that I feel deserves mentioning. Now, keep in mind that e is a number, not another variable. So, let's say we plug in e for the logarithm. That will give us logarithm base e of x. Now, logarithm base e is more commonly known as the natural log. So, if you weren't sure what the natural log is, now you know that it's log base e. Now, if we're to go through the formula for log base e, we have 1 over the natural log of e times x. Now, the natural log of e is 1, just as log base 10 of 10 is 1. So that means that the derivative of ln of x is 1 over x, because 1 times x is just x. Now, let's say we plug e into the base for the exponent 1. So that will give us e to the x. And going through the process, that gives us the natural log of e times e to the x. And, as I just mentioned, the natural log of e is 1, so that just leaves us with e to the x. So that means that the derivative of e to the x is e to the x, which is why e is so cool. Alright, so let's say we have one function, f, that we are adding to another function, g. Now, let's say we also want to find the derivative of this. Now that is quite simple. We simply split up each individual function, take the derivative of it individually, and then combine them both back together. So, what I mean by that is we take the derivative of the first one and add that to the derivative of the second one. Now, notice this prime symbol. That means derivative. It is the same thing as d over dx. However, the prime symbol is a lot easier to write, so I will use it whenever I'm working with functions. Now, let's give an example of this adding property. So, say we have x cubed plus x squared. So what we'll do is we'll split them up individually. So we'll take the derivative of x cubed, so that gives us 3x squared, and we'll take the derivative of x squared, that gives us 2x. And then we just combine them back together. So the derivative of x cubed plus x squared is just 3x squared plus 2x. Now, this also works if you're subtracting functions, because subtracting is essentially just adding a negative function. But let's say we were to do this with two functions that were multiplying together. So say we're multiplying f and g. Well, it's a bit different this time, a bit more complicated. We have to use something known as the product rule. So what that is we have the first function times the derivative of the second function plus the second function times the derivative of the first function. An easy way to remember this is first the second plus second the first. So let's get an example of that. So say we have x squared times sine of x. So what we do here is we take our first function and we multiply that by the derivative of our second function, which is cosine of x, and add that to our second function times the derivative of the first function. So, the derivative of x squared times sine of x is x squared times cosine of x plus sine of x times 2x. Now, just as there is a special rule if you are multiplying two functions together, there is a special rule if you are dividing two functions. So let's say we have f over g, and we want to find the derivative of this. For that, we need to use the quotient rule, which is even more complicated. So the process for that is we take our lower function times the derivative of our upper function minus our upper function times the derivative of our lower function all over the lower function squared. So a way to remember this is low d high minus high d low, draw a line, and square below. It's a nice little saying that has definitely helped me remember it. Now, to give you an example of how this works, let's take x cubed over tangent of x. So, we'll take our lower function times the derivative of our upper function minus our upper function times the derivative of our lower function. And that is all divided by tangent of x squared. So, the derivative of x cubed over tangent of x is 3x squared times tangent of x minus x cubed times secant squared of x all over tangent squared of x. Now, the last of the special properties I'm going to show you for derivatives is chain rule. And this is if we have one function inside of another function. Now, for an example, this could be like x cubed inside of secant of x. So this is what you do if you have one function inside of another. You take the derivative of the outside, with the function still inside, times the derivative of the inner function. There is no special saying, but it's a simple enough process that you should be able to remember it, should you ever need to use it. So, for example, we will take the derivative of the outside function, which is secant of x cubed times tangent of x cubed, and we'll multiply that by the derivative of the inside function, and the derivative of x cubed is 3x squared. So, the derivative of secant of x cubed is secant of x cubed times tangent of x cubed times 3x squared. Yeah, I hope you enjoyed it, hope you learned something, and see ya!